Hey students, good morning. Now here we are starting with lecture number 2 of kinetic theory of gases as you see. And in the first part I am going to discuss all the formulae which we have done so far or we know so far, so that we can get started with the numerical examples. So let me fire around. First is Boyle's law. Boyle's law says that pressure is inversely proportional to volume at constant temperature. That means the product of pressure and volume remains constant. That means if pressure is increasing, volume is decreasing, and vice versa. So we get the first formula: P1V1 is equal to P2V2. Thereafter comes Charles' law, which says that volume of given mass of a gas is directly proportional to absolute temperature. Please remember, I told you that in all these laws, it is compulsory for us to convert temperature from degree Celsius to degree Kelvin, whether it is mentioned or not. So, volume is directly proportional to absolute temperature says that V1 upon V2 is T1 upon T2, Charles' law. Next one, pressure of given mass of a gas is directly proportional to absolute temperature. That means pressure 1 upon pressure 2 is absolute temperature 1 upon absolute temperature 2. Now, you have heard about this in the past also at NTP, at normal temperature and pressure. The moment I use the word at normal temperature and pressure, that means I am allowing you to take the temperature as 0 degrees Celsius, which is approximately 273 Kelvin, because as you know, it is 273.15. Next, normal pressure is given by P naught. You can use P also actually, but P naught is better. P naught is pressure at 0 degrees Celsius. This is given by the formula HdG. H means height of mercury in barometer, D means density of mercury, and G is acceleration due to gravity for Earth. That means this is 0.76 meter or 76 centimeter or 716 millimeter. I have written meter over here of mercury. 13,600 is the density of mercury. Mind you, mercury is 13.6 times heavier than water. Density of water is 1000 kg per meter cube. Density of mercury is 30,600 kg per meter cube. Gravity is 9.3. So when we write this, the product is coming as 1.013 into 10 to the power 5 Newton per meter square. So please remember, when I say at NTP, means I am allowing you to take these two values as starter values. Now sometimes some conversions help you. Like 1 Newton per meter square, as you know, for pressure the unit is Newton per meter square, force upon area. And as you know, 1 Newton is 10 to 5 dyne and 1 meter square is 10 to 4 square centimeter. That is 10 to 5 over 10 to 4 is only 10. So 1 Newton per meter square is 10 dyne per centimeter square. So if I want to write this in dyne per centimeter square, will it not be 1.013 into 10 to 6 dyne per centimeter square? So this is the answer. Now, 2 extra units just for your knowledge. This unit called 1 bar. 1 bar. The word bar is come from barometer. Barometer is a device to calculate pressure. The way we have got thermometer as a device to measure temperature, likewise barometer reads pressure for us. So 1 bar is 10 to 5 Newton per meter square. So here if I want to replace this 10 to 5 Newton per meter square as bar, I can do that, and therefore I can say normal atmospheric pressure is 1.013 bar. 1.013 bar. Next, what torr? Now torr is come from Torrey-Series theorem. You are going to have this as part of your syllabus. The chapter properties of fluids. Right? There you are going to come across this word, and there is a theorem called Torrey-Series theorem. So torr is the abbreviation of that, acronym of that, and 1 torr is equivalent to 1 millimeter of mercury column. 1 millimeter. Right, now here as you see, it is 760 millimeter. So if you reduce this pressure to 760 as part of this value, then it becomes 1 torr. Next, if I am taking a vessel, or maybe I am talking about a river, or maybe I am talking about a lake, right? If I select a point on the surface of the lake, I should count pressure at this point as normal atmospheric gas pressure, which is the actual G. But if I select a point somewhere inside the liquid, then I should count its depth also, and the additional pressure will be HdG, where D is the depth, or H is the depth, small h is the depth, D is the density of water. D is the density of liquid inside lake. Okay. So the overall pressure at this particular point, which is highlighted in green, would be atmospheric air pressure plus pressure at this depth. So you know that as you go deep and deep and deep in the sea, as you go deep and deep and deep in the sea, the liquid pressure on the walls of the vessel, like submarine, ship, etc., is very, very high. If you are a very good swimmer, then also if you go deep into the water, you should go for earplugs because the surrounding liquid exerts tremendous pressure on its cavity. Okay, next, some standard values of molecular weights. You already know them. Now, sometimes they don't mention that. Sometimes in the problem they don't mention that. That is, you need to remember the standard values of molecular weights. And these are two very standard gases which you are going to come across in the problems. Hydrogen molecular weight is 2, helium molecular weight is 4, nitrogen molecular weight is 28, oxygen molecular weight is 32. Please remember, don't mix up between molecular weights and atomic weights. Atomic weight of hydrogen is 1, atomic weight of helium is 4, atomic weight of nitrogen is half of 20, which is 14, atomic weight of oxygen is half of 32, which is 16. Please be very careful. I am just only explaining this to you, but I have not mentioned it over here so that you are not confused. Right? Now from 9th formula, I am taking you straight away to 10th formula here, because later when I explain all these formulae, I am going to rub the simpler one and the older one. That means I am going to rub from 1 to 9. So I am going to use this part of the board to explain you some problems. So here I come on 9.1. You know that 1 kilomole of any gas is n kilogram of that gas. And what is the meaning of n? Molecular weight. What is the meaning of n? Molecular weight. So 1 kilomole of any gas is n kilogram of that gas, and n0 molecules. Where n0 is Avogadro's number. N0 is Avogadro's number. And I would like to mention the value of that. As you know, it is 6.03 into 10 raised to 26 molecules per kilomole. Please remember, in chemistry they keep talking about molecules per mole, and therefore in chemistry most of the time you will see power of 10 and 23. But in physics we normally prefer kilomole. So it is 10 is to 26. Next comes ideal gas equation. PV is equal to nRT. Right? Where n is number of moles or number of kilomoles. It is given by mass of the gas upon molecular weight, or number of molecules upon Avogadro's number. I repeat, it is mass of the gas upon molecular weight, or it is number of molecules upon Avogadro's number. These are different styles of writing ideal gas equation. PV is equal to nRT can also be written as P, only P, mind you, this was P, this is P. As rho bar T upon n, where bar is universal gas constant for 1 kilomole. Please remember, capital R is universal gas constant for 1 kilomole, and it is 8314 joule per kilomole per Kelvin. It is same for all the gases. But if I write chota r, it is bada R upon bada F. That means it is universal gas constant upon molecular weight. It is called universal gas constant for 1 kilogram of a gas. This was for 1 kilomole, which is same for all the gases. This was for 1 kilomole, which is same for all the gases, but this is for 1 kilogram, which differs from gas to gas because molecular weight differs from gas to gas. So please remember, capital R is universal gas constant for 1 kilomole of a gas. There is small r, which is capital R upon n, is universal gas constant for 1 kilogram of a gas. Capital R is same for all the gases, small r differs from gas to gas. Next, the way we have capital P, small n, capital R, capital T. Likewise, we have capital P, capital N, small kT. Here, small n is number of moles or kilomoles, but here n is number of molecules. K means Avogadro's number, which is R upon N0, which is universal gas constant upon Avogadro's number. This is Boltzmann's constant. K, I'm so sorry, few seconds back I mentioned it as Avogadro's number, I'm so sorry. K is Boltzmann's constant, this is R upon N0, which is universal gas constant upon number of molecules for 1 kilomole of a gas. Next, In the previous lecture, that is 1C, we came to one very important conclusion. Pressure exerted by a gas is 1/3 rho C square. 1/3 rho C square. So what do I mean by C square? So let us come here over here. In formula number 12, I am discussing three sub-formulae: mean velocity, mean square velocity, root mean square velocity. Mean velocity is the average velocity of all the gas molecules. Now here the problem with mean velocity is might be zero. Suppose I have got four molecules and their velocities are 1, 2, -1 and -2. Because you know that velocity is a vector and therefore it can be negative. So here the answer is 0. Now this is little awkward situation because mean velocity mathematically is coming at 0, but physics wise it can never be 0. Because the gas molecules stop moving only at absolute 0, only at -273.15 degrees Celsius. And nowhere in the universe this temperature is there. That means there is something wrong. Right? Now when you come across this kind of a situation in physics, what you should simply do is, in place of taking average of velocities, you take average of squares of velocities. Squares of velocities. So now the name is mean square velocity. Square. You know that square of a number can never be negative. So this answer can never be 0. Right. But then now the new problem is, mean velocity, the unit was meter per second. Mean square velocity, the unit is meter square per second square. I want to come back to meter per second because I am interested in velocity. So I should take the positive square root. I should take the positive square root. So mean velocity, mean square velocity, root mean square velocity. Here I am so sorry. I should write square root also. I should write square root also. So this is root mean square velocity. Back to this formula. P is 1/3 rho C square. Rho is mass of the gas upon volume of the gas. This is mass of one molecule into number of molecules upon volume times C bar. Solving this equation, solving 14th equation, we come to 15th equation, which is another very important equation, and that is the expression for mean velocity, root mean square velocity. This formula is going to help us like anything in solving problems, which we are going to start in a few moments. So root mean square velocity is given by root of 3RT upon m. 3 is a number constant, R is a number constant, R is universal gas constant. So RMS velocity basically depends on two things: absolute temperature and molecule. If the temperature is more, molecules move faster. I repeat, if the temperature is more, molecules move faster. On the other hand, if the gas is heavier, the molecules move slower. Right? And finally, if the gases are different, and if the temperatures are also different, then RMS velocity depends on root of temperature directly and root of molecular weight inversely. And finally, before I start with the problems, right? For sub-formulae, one is for kinetic energy per kilomole, which is very, very, very important for you because once you remember that, the kinetic energy per kilogram is very easy, kinetic energy per molecule is very easy, and kinetic energy per volume is very, very, very easy. So, the first one, all these things we have derived from P equal to 1/3 rho C square only. Kinetic energy for kilomole of a gas. Kinetic energy for kilomole of a gas is given by 3/2 RT. 3/2 RT. Now, if this is the kinetic energy for 1 kilomole of a gas, then indirectly you can say this is the kinetic energy for n kilograms of a gas, or this is the kinetic energy for n0 molecules of a gas. Because from formula number 10 we know that 1 kilomole means n kilogram. N means molecular weight, mind you. And or means n0 molecules, which is Avogadro's number. So if this is the answer for n kilogram, what is the answer for 1 kilogram? Obviously divide by n. I repeat. If this is the answer for n kilogram, then this is the answer for 1 kilogram. Divide by n. So it is kinetic energy per kilogram. Again, if this is the answer for n0 molecules, Avogadro's number, then what is the answer for 1 molecule? Divided by n0. Right? Lastly, capital R upon capital M is small r, and capital R upon capital N0 is K, which is called Boltzmann's constant, and its value is 1.38 into 10 to minus 23 joule per Kelvin. Joule per Kelvin. And at the end of the list of formula, I have written what is the meaning of. Just a minute. I would like to just take a picture of this. Yeah. At the end, I have written what is the meaning of capital R, which is universal gas constant for 1 kilomole of a gas, and what is the meaning of small r, which is universal gas constant for 1 kilogram of a gas. Mind you, this question has come as a multiple choice question, that capital R is same for all the gases, whereas small r differs from gas to gas, molecular weight of different gases being different. So, here is the time for us to start with problems first, and then we will switch over to the multiple choice questions. But before I do that, just quickly revise this list of formulae, which is going to help you like anything, because I am going to rub some part of the board so that I can explain problems to you. Right? And would you please excuse me for a minute? Before I start it, to be, just excuse